Hello everyone, welcome to another problem session. So we are going to do a problem in using law of refraction today. This is a very standard problem. All this is standard but has interesting geometry involved here. Okay, so let's look at the setup. You have a rectangular plate, so that's the plate. So you have this is a rectangular plate, and width is W, and height can be anything. I didn't give you height, and it's three-dimensional, so it's a little bit thickness is not of importance here either. So ray will come from, say, this direction. A ray comes in, and it doesn't continue on the original path because of the refraction here. It refracts and another refracts. So there are two refractions. One at O and another is at O prime. Now, if the refractive index of this plate is greater than N1, then it's going to bend inward. And that's because of Snell's law. And then when it comes out, now this is bigger than this, that's going to bend outward. And if these guys are same medium, then what comes out is going to be parallel to what it was going to be originally. So that's what this is. If this is not the case, then it's not going to be parallel. And we are not going to do that case. We're just going to do N3 equals to N1. So there are only two refractive indices here. And why would it be parallel? Well, if you look at O, you have a N1 sine theta 1 equal to, if this is the same normal, so let's call this theta 2, is N2 sine theta 2. And over here it do a normal again, because these are parallel, these normals are parallel. So this angle will be equal to that, theta 2 again, this angle will equal to theta 2. So this will be N2 sine theta 2 on this side, and on this side, say this call is theta 3, N3 sine theta 3. So if this is equal to that, then this will be equal to that. And so this will be parallel. That's the reason we're parallel. So now it's parallel, then where it was going to be and where it goes, they're laterally displaced. And this distance, perpendicular distance, that's called lateral displacement. I'm going to use a letter L for it. And that's the one I want to know. So the question is find L for given theta 1 and N1 and N2. So that's the question. So maybe you can work it out. There can be many different ways to write the final answer. So we'll just work out one ourselves. So you can pause the video and work it out, and then come back and look at what I've done. Okay, so what will be my strategy? My strategy is based on finding this. Okay, so if you look at in this area, so you have the original direction and actual direction, and then this distance is W. So so if I can so over here, this is the path it takes. Suppose I could somehow find this delta, then this direction and this direction, if you look at a triangle here, so if I can find this, then let's put perpendicular here. So if I know this delta, and if I know one of these angles, say I know this angle, say phi. So in that, if I know, suppose I don't know, we'll figure out how to get phi, and this is delta, then this will be just delta sine phi. This angle is phi. Delta times like that, right? So how do so it comes down to finding delta. So this will be L, because this is 90 degrees, and so it comes to finding this thing and finding this thing. Okay, so let's go back. This is going to be theta 2, and from here, from here, this was theta 1, so this will be theta 1, because this line is same as, and this line is same. So this angle has to be equal to this bigger angle. So in this triangle, this thing is theta 1 minus theta 2. And so it's like that. So that's one thing we find. This is theta 1 and this is theta 2. So if this is W, then using theta 1, this will be a W times tangent theta 1 and theta 2. This is theta 2 down here, and this is theta 1. So but this bigger one is angle theta 1. So this will be W tangent theta 2. So the delta is very easy, is difference W tangent theta 2, theta 1. This is theta 1, theta 1. The big angle is theta 1 minus W tangent theta 2. Now let's look at that. So if you look at if you look at this whole triangle, so now we're going to find out what the phi will be, right? What this, either phi or that angle, we need to figure out phi. Okay, so I drew some picture here. So this is theta 2. So, and this is 90 degrees. This was the W. And so this corner angle will be 90 degrees minus theta 2. And so this angle here will be the same as this angle. And this is right angle triangle, so this angle down there will be 90 degrees minus 90 degrees minus theta 2, which means theta 2. So in this triangle, phi is actually theta 2. So this is delta and we want L. So we got, this is theta 2 and this is delta, and the L we want. So L equals to delta, because, let me see, this, so actually this is base, yeah, the L is base, so actually cosine, probably this is base, right? So this angle will be cosine phi, not sine phi. That was wrong. So cosine theta 2. Okay, so we have an answer, but we got things like both theta 1 and theta 2. cosine theta 2. So I could just multiply this out, or we can say W tangent theta 1 cosine theta 2 minus sine theta 2. So we need to write everything in terms of theta 1, there's no theta 2. That means what we'll have to do is use, so this thing would turn out to be W tangent theta 1 cosine theta 2 will simply be see n1 sine theta 1 is into sine theta 2. So sine theta 2 is n1 over n2 sine theta 1. From there we can write cosine theta 2 will be square root of 1 minus n1 over n2, this is square sine square theta 1. So that's this guy, and this guy will be this stuff, n1 over n2 sine theta 1. And so that will be answer. So it's clearly you can write it in multiple other forms, but this is one of the expressions you can get for the lateral displacement. Now if you have numerical values, you can just plug in there, and it depends on, interestingly, it depends on the angle. So it's obviously true if you had sent, instead of this way, if you suppose you sent the ray this way, the displacement is 0. So when theta 1 is 0, it should be 0. So this gives me 0 and this gives me 0. Clearly, right? Now if I had sent the ray this way, so theta 1 is 90 degrees. It will never make it that side, right? So theta 1 is 90 degrees. So nothing happens to here, nothing happens to here, but look at this. Tangent theta 1, 90 degrees is going to blow up. So this will blow up, and this will be 1, this will be 1, and this will be 1, but this will blow up to infinity. So this will kind of dominate, and it just shows that it becomes not a feasible solution, that the path comes out like this. So that's this one problem here. So this angle has to be less than, so theta 1 has to be less than 90 degrees. Otherwise this physical situation doesn't make sense. Okay, so I'm going to stop here. Next thing I'm going to do is in same kind of displacement, but angular displacement, not physical displacement, and for that where the prism has to be of a different shape and kind of prism we're going to use. So next we're going to do the displacement in a prism like this. So if I send a ray like this, it's going to come out instead of going in that direction, because the prism cut is going to come out in that direction. So you can see this angle. What's the angle between the original direction and the new direction? So if you move it backward, so that angle. So we're going to work out a formula for that angle and how to think about that. Okay, that displacement is called because of deviation, so it's called angular deviation of a prism. We're going to do that in the next lecture or next problem. Okay, for now, if you like this, you can hit like or share, tell your friends, check out my website, and subscribe to this channel. Take care. Bye.